Hi everyone, in this video we're going to solve some more complicated exponential equations, but we're still going to be using these same two main tools from the last video. The one-to-one property, where if I have a base, the same base, and two different exponents that are equal, that implies that those two things in the exponents are the same. And also this inverse property, where if I take a log of an exponent where the base of the log is the same as the base of the exponent, I'm just left with the thing in the exponent. So these are the two that I'll use most. Okay, so let's get started. Here is our first example. I have e to the minus x squared equals e to the minus 3x minus 4. So you might notice I have the same base and different exponents, so I can just set those exponents equal to each other. So far I've used the one-to-one property. And now it's not an exponential equation anymore. I've gotten the variables to just be not in the exponent anymore. That's the main goal in all of these examples. So now I can just solve this as I would any quadratic equation. So I want to have all of my x's on one side and 0 on the other, and then I'm going to factor. So let's bring this x squared over. I'll have 0 equals x squared minus 3x minus 4. And now I'll solve this by factoring. So this factors as x minus 4, x plus 1. So I've factored. And this means that either this term equals 0, in which case x equals 4, or the second term equals 0, in which case x equals minus 1. So those are my solutions. And I just want to point out that in this example, we didn't have to use the one-to-one property. We could have used the inverse property, because if I take a natural log of both sides of this equation, then the inverse property says that if I take the natural log of e to some power, I'm left with whatever's in the exponent. So on the left, I'm left with negative x squared because the ln and the e undo each other. On the right, the ln and the e undo each other again, so I'm left with minus 3x minus 4. And it's the same thing. So this is using the inverse property and taking log of both sides. So that's the strategy we'll use in every single case from now on. The one-to-one property is just sort of a shortcut. Okay, so in this next example, I'm trying to get at this x in the exponent. The 3 is sort of in the way, and the 2 is the base of the exponent, so I can't do anything with that right now. So my first step is going to simply be to divide both sides by 3 to get that 3 out of the way. So I'll have 2x equals 42 divided by 3 is 14. So all I've done is divide by 3. Now, what I need to do is get this x out of the exponent and get it to be just part of the equation down here. So I'm going to use the inverse property. So I'm going to have to take a log of both sides. The base of the log is going to have to be the same as the base of this exponent. So if I take log base 2 of both sides of this equation, then I have log base 2 of 2 to the x equals log base 2 of 14. So log both sides. And now if I have log base 2 of 2 to something, I'm left with just that something. So x will equal log base 2 of 14 by the inverse property. So let's continue. Here I have e to the x plus 5 equals 60. So I need to get at this x. So let's try to isolate it. The first step toward isolating it is isolating the whole term e to the x. Sort of like in our last example, the first step toward isolating 2x was getting rid of this 3. You can sort of treat the whole exponential term as the variable, and then we'll take a log of both sides at the end. So my first step is going to be to bring over the 5. So I'll have e to the x equals 55 just by subtracting 5 from both sides. Now I still need to isolate this x, so the way that I do that is I log both sides. And I choose the log to have the same base as the base of the exponent, so I'm going to have to ln both sides. I do that because now the inverse property applies. Ln of e to the x is just x, so x is ln of 55 by the inverse property. This next example, the fourth, looks slightly more complicated, but it's not at all. This is the term with the exponent. I'm trying to solve for t. So my first step is going to be to isolate the exponent term, just like it has been in the last two cases, but this one I'll have more steps. So first, I'll bring over the 4. So that gives me 15 on the right. Then I have to divide both sides by 2. So first I added 4 to both sides. Now I'm going to divide by 2 on both sides. So what will I have? 3 to the 2t minus 5 equals 15 over 2. Now I'm at the stage where I can almost solve for t, but I can at least solve for the exponent using the inverse property. So this is where I'm going to log both sides. I can't move any other numbers around without taking a log. And what should the base of my log be? The same as the base of the exponent, so that the inverse property applies. So take log base 3 and log base 3. Log base 3 of 3 to a power, I'm left with just that power. So this is what I'll be left with by the inverse property. So 2t minus 5 equals log base 3 of 15 over 2. And now I just solve for t. This is simply a number, so let's just leave it in this form for now, and we'll estimate it using our calculator in a moment. So I'll bring over the 5. 2t equals log base 3 of 15 over 2 plus 5. And now to get t by itself, I just have to divide both sides by 2. So in all these steps, I'm just solving for t. And I can put this in my calculator to get an actual solution. So my numerator is going to be log of 15 over 2 base 3. So remember that we do that by doing log of 15 over 2 divided by log of 3. That's the change of base formula. Also in my numerator I have a plus 5, so I'll add 5 and close the parentheses for the numerator. And I divide the whole thing by 2. So this is approximately 3.417. And I have just one more example for you. This one is a really important example because it's a lot trickier than the ones that we've seen. So here I'm trying to get at the x, but this 2 is not e to some power, so I can't just use the one-to-one property and factor like I did in this first example. But I am going to use factoring. So if this is my original equation, the first thing I'm going to do is write it in quadratic form. So the way I want to think about this is think of e to the x as our variable. And we'll try to solve for e to the x first, and then we'll take a log of both sides as the end. So if e to the x is our variable, then we can think of the first term as e to the x squared. The second term is just 3e to the x. And the last term is still 2. But now it's like we have something squared minus 3 times something plus 2 equals 0. This is just a quadratic equation. And so we can factor it in a special way. The first term of each has to be e to the x squared. So I know that each of these should be e to the x. So on the side, here's our scratch work. We're imagining this as y squared minus 3y plus 2 equals 0, where y is just e to the x. So let's factor this one first. This is going to be y and y. This term and this term have to multiply to 2 and add to negative 3, so it's going to be minus 2 and minus 1. And that's how this one should factor as well. This term and this term have to multiply to 2 and add to minus 3. So I have minus 2 and minus 1. So now what I can do is set each of these equal to 0. Just like I would in this case, I would say, so y minus 2 equals 0 or y minus 1 equals 0. So in this case, I have e to the x minus 2 equals 0, or e to the x minus 1 equals 0. In this case, that means e to the x equals negative 2. In this case, e to the x, positive 2, e to the x equals 1. And now, finally, I can take a log of both sides of this equation to get my final answer. So I take the log that has the same base as the base of the exponent, so I'll ln both sides on each of these equations. So on the left, I have ln of e to the x equals ln of 2. On the right, I have ln of e to the x equals ln of 1. Now by the inverse property, ln of e to the x is just x. So I have x equals ln of 2, or x equals ln of 1. And we know ln of 1 equals 0. So those are my options. So this is a complicated example, I know, but it makes a lot of logical sense. We think of e to the x as the variable until the very last step, and that's when we ln both sides. So you're basically just solving a quadratic the way you normally would, and you have one additional step of taking the ln of both sides in order to get x. So I hope that these examples were informative and kind of fun, and let me know if you have any questions.